So we start with this experiment. Say that I'm choosing a matrix A from uniform distribution, elements coming from ZQ, and matrix M cross. It's a matrix. And choosing a vector again from uniform with dimension n.
Turn the lights.
So it'll be a,
Maybe we can turn it on. Yeah,
so yeah,
it's fine. Just try to write little.
more down.
Yeah.
So you're choosing a random matrix uniformly, where the entries are from ZQ of dimension m cross n, and a vector again of dimension n and from its elements are from ZQ. So if I output A times B, does this look random? In fact, yes, it looks random because you just take a random combination of random columns of this matrix, and then obviously it'll be random. In fact, if we take A times E1, and E1 is just 1 and then rest of them zeros, this is also random, right? Because the first column is obviously random, and you're just outputting it. But what about this? I output both A and A.
Because they share the same first column.
Yes. So if you look at the distribution of this, the first column, the last column will be same. Right? This is what E1 is doing. It's just outputting the first column. And so
That is a matrix, that is a vector.
this, yeah, the same. But this last vector is dependent on its matrix, and you can see it also. It's like just the first vector being rewritten. But what about A comma A? Where or A B? What do you think? It looks random, right? So, but now, so this is like one extreme case, this is like another extreme case where the coefficients that I'm choosing is truly random over here. Here it's like just fixed all the time. So what do we say when I'm choosing this coefficient vector from the distribution, which is close to uniform? Again, intuition says that yes, it will look somewhat random. And what leftover hash lemma says that if you know that this distribution has enough entropy, that is enough randomness, at the same time the number of columns in A is bounded below, then this will look random. It will be close to uniform distribution. So extractors is something like this. You have these truly random bits, so A is uniformly random. Yeah? So it's like truly random bits, and you're getting this, something like not very random, but not bad also. And you're trying to output a almost uniformly random vector, almost random vector, which is AS. So it's like kind of extracting, the random bits from A and S and producing a new one. That's what an extractor is. A strong extractor.
So I don't need the system of writing A, AS. Right?
So consider this as a matrix of
Like an additional column.
yeah, addition column. Right.
Okay.
Right. So I keep saying close to uniform, yeah.
So AS is random, right?
If S is like a zero vector.
A is random.
A is random, S is not random, it's coming from a different distribution.
Yeah,
But so
so
say
you are fixing it.
so look at an adversary can see A as well as AS. So in this case, look at if an adversary can see this distribution, he knows that in this one, the last column will be always equal to the first column.
Adversary knows it, then it is not.
Yeah,
random.
he's seeing A also.
A is not random.
But what left hash will say that even if the adversary sees A,
Okay.
for him this one will look like a truly random vector. Not a truly random, somewhat random. Statistically, it will be random. So the adversary can't distinguish whether this is of this type or if it's like U, comma.
You cannot predict AS.
Correct. So,
You are giving this as a matrix.
matrix, yeah. Okay. So yeah. So now we need to define a notion for closeness of two distribution, because I'm always talking about it's close to uniform. So I'll be using this definition of statistical distance. So statistical distance of two distributions, let's say D1, D plus. Okay, the sample space should be same. Is equal to so what it's doing is just, like if you look at this probability vector of this distribution D1, probability vector of this distribution D2, you're just taking the L1 down. That's it. Any doubts in this definition? So you look at the element X in each, the probability given to element X in D1 and D2, and look at the difference. So,
And what if it is continuous?
that's it.
What if it is continuous? D?
It's-
Uniform is continuous, no?
Huh? It can,
Uniform is continuous.
yes.
Yes, can take all possible values.
This is uniform on a finite set.
Let's take a finite set. Let's work with finite set for a minute. So we know that the statistical distance is and what will be the upper bound? 1, because if it's exactly equal, if D1 is equal to D2, everything goes to 0. And so it's at least 0, and at most 1 if it's like a disjoint distribution. See that? So probability 1 plus 1 and then becomes 2. But see, this definition is pretty strong definition. So if you give you two distribution, okay, again I can't give you a distribution because like it might have lots of elements, so you'll be only allowed to sample from this distribution. It'll be very tough to study the probabilities to given to each element.
Is it half or
Half.
n?
Half of 2 to 2. So yeah, so it might be very tough to find this value. So we'll use a weaker notion, which we call the min entropy. So min entropy of a distribution. So let's say a random variable for that distribution. What it says is, you look at the probability, the highest probability given to an element. Take its log. Since probability is less than 1, it will be a negative term. Minus of this. Okay. What this says is, so just look at this probability distribution. If one element has very high probability, okay, that itself says that it's not random, right? Because there's one element who's getting like too much weight, and the rest of them are like less. So if everyone's having equal, then it looks like random. So that's what it's saying. So now this is, you can see that this is much easier than this, because if you know that one element has high probability, then you know that it does not have that much randomness. You understand?
High or low?
High, or at most it can be like everyone's having equal probability. Ashish?
Definition is okay, but basically, I'm not sure about the utility because one element might just bias everything.
Every element?
One element might bias everything.
Bias in the sense?
If one element has a high probability, others have equal probability, then the entropy will become very high.
Yeah, the entropy will be very high. So, no, the entropy.
The entropy will be high, but the
But-
min entropy will be low.
Yeah.
The min entropy will be low.
So
Yeah.
it influences just by one.
Will be 1, can be 1. Yeah.
It
So,
influences by just one weight. It influences by just weight of one item. That's it.
the one item, yeah, if you put, yeah, kind of that one. So, yeah, as you said, you can give like, for one element, imagine I give like probability 1. So you have this lower bound as 0, and the upper bound will be, say, the sample space is like 2 raised to n, then you have n. Then everyone is given 1 by 2 raised to n weight equal. Okay. Now let's go to the definition of extractors. So what extractor is, it is a function which takes input, an n-bit string and a d-bit string, and outputs an m-bit string. Okay, and okay, I call this extractor a k comma, this function a k comma epsilon strong extractor. If for every random variable whose mean entropy is at least k, that is, I'm saying that this distribution has enough randomness. Okay, then this distribution, that is, you're taking a, so think of the second part as a seed to this extractor. So you're giving some truly random seed to the extractor, taking some almost random bits from this distribution. Okay, that's the output of the first part. And the second part is again the same seed that you used over here is repeated over here, and this is. So what this means, that is, I say D1 is epsilon close to D2, this is just the definition of statistical distance. So if the distribution has some enough mean entropy, see, the more the mean entropy, the more random it will become. Okay? And then, if I can use some truly random bits and this almost somewhat random bits, then the collection of these two will look random. So I have the initial D bits of randomness. I'm also outputting some, because its output is m length. I'm outputting some m length string. Collectively, both of them looks random.
So this is stronger than just requiring the output to look random, right?
So that's why I wrote strong.
Okay.
Wait. 3 dots.
What do you mean by that epsilon close?
Yeah, epsilon close, because the statistical distance will be bounded by epsilon.
Okay. How is that coming about?
No, this is the definition.
Oh, okay.
I call an extractor a strong extractor, K epsilon strong extractor, if the distribution has enough entropy, that is K, at least K, and the statistical distance is bounded by epsilon.
Okay.
Okay, now we can go to, actually, yeah.
Why add that UD?
That's what he said. So, if I don't show this,
Oh, then
yeah, then I can just simply output UD over here, or something like that. But I'm showing you UD. Apart from UD, I can still construct more random bits. That's why it's kind of extracting out things to random bits. Okay, so we need one more definition, which is a universal hash function. Or hash function, family of universal hash functions. So, the family of universal hash functions H is family of hash functions is universal if for every x comma y that belongs to comma n, so a family of hash functions, H, okay, H contains some family of hash functions. It is called universal if you take this any two random strings, the probability that both of them will collide is bounded by 1 by 2 raised to n, where m is the output of the hash, output length of the hash. It's just saying that the number of collisions in each bucket is kind of balanced. That's it. Nothing more you have to know. So there's like you randomly pick any hash function. Then if you see these two strings,
So what is M over here?
M is the output of this function.
The length of
All
the
hash
function.
Yeah,
Okay.
0, 0,
Zero,
1.
comma one.
Okay. That's
You can write h goes from 0, comma
Yeah, I
1.
can write that. So then, okay. Now, leftover hash lemma says that. Okay.
We need x not equal
There
to y.
exists
So-
h.
We need x not equal to y.
X, yeah, I think so. You need that. Yeah, this is that.
Otherwise,
Yeah, it's not quite. X is not. So leftover hash lemma says that okay. So let x be a random variable with the mid entropy being equal to k. Okay, and say epsilon is some constant greater than 0. Then if h is a universal hash function, hash family, with output n, which is having this value, then the extractor which I define by so the extractor will take as input a hash function from the family and an input for that, and just output the hash value. Okay. This is a k comma epsilon strong extractor. And x should come from x and hash function to the hash function.
so is it a description of the function?
Yeah, so your extractor is nothing but you take a hash function, an input.
And that h small h, it's a description of the function h, right?
Yes, yes. So yeah, it should be like input should be a string, right? So you have this. Yeah. So this h over here is just the index.
Yeah.
Is this index? And so you're just choosing randomly. So when you're choosing randomly, so I think I should mention one more thing. So of size 2 raised to b. So this h contains 2 raised to b hash functions. Okay, so that's why there's a d over here. Okay. So you pick any one of them. That will be your truly random picks. X is coming from this distribution, and this will be a strong extractor. K epsilon by 2. Did you guys understand the lemma? Huh? Is it yes or is it no?
Yeah, it seems easy to believe. I mean,
Okay, I didn't know about that. Yeah, actually,
So hash function keeps distinct, I mean, with high probability.
yeah, there will be less
keep
collisions.
distinct. So
No, not less. It will be like kind of balanced collision. No bucket will have a lot of collisions on an average.
and in extractor, we want that it is epsilon close to uniform. Okay, uniform.
Just giving out random inputs is basically what we are saying.
It's kind of, yeah, giving kind of,
Close to.
yeah,
Yeah,
close to.
given
Even
that.
after seeing the, yeah.
Okay.
Even after seeing.
So we'll also be
H.
giving h, yeah. I just use this capital notations to just talk about powers of the smaller letters. Okay, so let's go into the proof. So, let's define something called a collision probability. I think it's still stuck.
Yeah, no, that's fine.
I think everyone's still staring over there, so yeah, we'll just clear this.
Yeah. No, I was just thinking of
Hmm.
this function you are defining as the extractor
Yeah.
has two things, right?
Yeah. What does this C?
So, yeah, so what
See,
that is the function h, right?
No, it's the index of the function. So h will be like
Okay,
h1 to
as
h2
an index.
raised to
Okay,
b.
okay, fine, right,
So like that. So I'm just abusing the notation. Sorry. Yeah. And
right.
x is yeah.
I was
the
just
index.
stuck with that abuse.
Oh,
So,
sorry. So, so what does collision probability say is that so you have this random variable c. So you sample twice from this distribution independently. What's the probability that it could happen? So probability of, so if you take another random variable z dash, which is identical to z but independent, then this one. So this is exact. This is nothing but summation probability of z equal to z square, because they're independent. Z and z dash are independent. This is the collision probability. So let's look at the collision probability for h of x, comma h. Again, abusing the notation. This means like, but over here I'll be using as hash functions itself, but it's actually just the index, the hash function index. So what does this say? It's saying that you're taking the summation over h1, h2, this is the hash function, x1, x2 of x, probability that h1 of x1, comma h1 equal to h2 of x2, comma h2, right? Collision probability. Okay.
Two random variables.
Mhm. Now, so
that is in the case of truly independent, but here you will.
no, so collision probability is defined very much. Collision probability is defined by two independent random variables colliding.
So these are random, independent and h1 and h2.
Yeah, h1, h2, x1, x2.
Hmm.
Now, again, so this is, you can write it as h1, h2, x1, x2, probability of h1 equal to h2 times probability of the same thing given h1 equal to h2. Because if h1 is not equal to h2, obviously it won't be equal, right? So the second term and the second term should be equal. So that means h1 should be equal to h2.
Mhm.
If it's not equal, that will be 0. Right. Now, so this one again can be written as summation probability of, let's open up this term. Probability of, so this is h1, sorry?
H1 equal to H2.
Yeah. Given x1,
H1 x2. So h1 is equal to h2.
yeah, let's say that. That's what is condition over here already. I'll put the condition. h2, comma, x1
Not equal to h2.
not equal to x2 into probability of x1 not equal to x2 plus then no, actually probability of again this one
H1 equal to H2.
x1 equal to x2 given h1 equal to h2 comma x1 equal to x2 into probability of x1 equal to x2. now, if h1 is not equal to h2, x1 is not equal to x2 and h1 is equal to h2, we know that h is what? It's coming from a universal hash family. So this probability is bounded by 1 by 2 raised to n. So, and what is the probability that h1 is equal to h2? It's uniformly random, yeah? So it's 1 by d.
1 by 2.
Capital D. Times this first term will be n. And actually we'll put upper bound, right? Because this structure is just equal to probability equal to 1. Over here,
You still have the summation.
it still has summations. Yes, it still has summations. Well, we still have it. Actually, I don't want the summation over there.
You can use the union bound, right?
Oh no, you won't.
You won't be having, right? Because okay, yeah, this one happens with probability 1 by d. I'm taking it outside.
Yeah, right. After you move, yeah.
Yeah, this is
okay,
uniform.
yeah.
Taking all the summations of this one will become 1 again.
Right, yeah.
And over here, so this is probability 1 because your hash function is equal, the input is equal, so this probability will be 1. What is this? This is like collision in your x. And what is the, and x is having min entropy k. So this is become 1 by k. Okay.
Actually, how are you getting this whole big term inside?
Just because I'm just conditioning over here. So
Conditioning on h1 equals to h2.
x1, x2. Yeah. x1 equal to x2, x1 not equal to x2.
Okay.
Breaking
Break out, break out.
two disjoint events.
So now, also I have this.
What happened to some items?
Huh?
What happened to the sum?
So this one I can take it out and then. So this one's. This one is. This is the collision probability. Again, I can take it out. Summation of this one will become 1. Similarly, here summation is 1, and this one is collision for the distribution x. Yeah.
So you are only focusing on the first term.
I'm focusing both the terms. So now again, I just use this value over here for k. So this will become 1 by dn 1 plus h1 square, right? Just power both sides by 2 and just bring it. Right? So now we want to show that it's a strong extractor. I think I love the definition, but so what we need to do? So yeah, actually, this thing. We need to show that the statistical distance between these two is bounded by epsilon by 2. So rather than looking at the L1 node, first we'll do the L2 node and then bound it using that L2 node. So I just call that difference vector as V. So this one is equal to what? So IP hash and the output of hash probability that so h of x equal to h of x, comma, and then capital H equal to h minus your, for each of them it is probability that um equal to h of x, comma, ut equal to h. So
In above it should be UD equal to H, right?
sorry, which one?
The first term. There also should be UD equal to H.
No, this is for the this term. So the output is this one.
Right.
That is what h of x.
Right.
And then this is the seed, which is being used, which is h, the index of h. That's the thing. And we need to put a square also. So this is equal to again summation probability of h of x plus what is this square? So this is like uniform. How many elements are over here? 2 raised to m, 2 raised to d. So 1 by d square m square. And then 2 times, so minus 2 times probability of this into probability of this. What is the probability of this? It will be 1 by dm and then this probability. And this, not writing the whole thing. Okay, this is what we want. So putting the summations inside. Okay, putting the summations inside. This one will become 1 by dm. This one, okay, this is a constant. Putting summation over there, this one should go to 1. This is minus 2 times dm. What is this? This is nothing but the collision probability. So this is 1 plus epsilon square by dm. So actually it's bounded up, bounded by this one. So this is equal to epsilon square by dm. Any doubts? Now the rest is trivial. So that is your statistical distance, which is the L1 norm, is what? The summation each vi, but it should be the modulus, the absolute value. This we can write it as v comma u, where u is either plus 1 or minus 1. If it's negative, it becomes minus, plus. Then by Cauchy sorts, it is v and u. V is by epsilon square by rho dm. This one's length is dm, so and statistical distance is what? This one divided by 2, so got extra bit. Okay. So the application which I'm going to show is actually it's based on lattices. Okay. So does everyone know lattice? Okay. So a lattice is defined by a basis, which is nothing but taking just integer combinations of the spaces. Say the basis is n cross n. So see that this is not a vector space. In vector space, you can shorten a vector, you can do division in a vector space. But over here, it's just additions, nothing more you can do. So it's like discrete points in the vector space. Kind of a discretized version of a vector space.
Sorry, what is B again?
B is the basis of the
Any
space.
basis.
It can be any basis.
Okay.
And yes. So what Aita showed is that, so there's something known as, so since this is discrete points in space, you have a non-zero shortest vector. So there is, obviously there will be a zero vector over here. Apart from the zero vector, then shortest vector. That is known as the shortest vector of the lattice. And that is actually a very hard problem to find a shortest vector in a lattice. What Aita showed is, if I look at a lattice, which is of this kind, all the vectors such that A times V is equal to 0 mod P, or 0 mod Q. Just believe me, this is a lattice, okay? Then if you can solve the shortest vector in this lattice, then you have an efficient method to solve shortest vector in any lattice. And this gave birth to lattice-based cryptography. So you are relating the average case hardness of SVP to hard case, worst case.
And that lattice thing, why are you
want discrete points, right? So if it's like Q, then again, you kind of have like, it's not discrete. You can do divisions in Q, right? In integer, you can't do the division.
Okay.
In Q we will get sorry,
Yeah,
close to
very
zero.
close to zero. Exactly.
So, yeah, what really is special about this lattice?
For that, I'll take another talk on this direction.
No,
but
just an intuition maybe. Like, why do we?
let me see how. I think the intuition itself will be pretty long.
Yeah, maybe we
we'll
can take it
offline.
offline.
We'll take it offline. So,
This is
so if you can solve this,
this is also lattice.
So it's a
not
family
Q,
lattice.
discrete ZQ.
yeah, it's in ZQ. No, it's actually in Z. It's in ZX because integer vectors we can be
A
integers.
is basis. A is
A is some matrix, not a basis. It can be some matrix of n cross n dimension. Let's say
Sorry, what is
A is a randomly chosen matrix. So its family of hard lattices is you choose a random A matrix, and the lattice defined like this. This is hard lattice. So on an average, if I give you a lattice like this, and if you can solve the shortest vector in that, not exact shortest, some polynomial approximation of the shortest vector, then you can solve SVP in any lattice, Euclidean lattice.
So average and worst.
Worst.
So, is this matrix defined over some field from where this Q is coming? What is this Q and how is it related to A?
These are things that
integers, right? Q's and some integer, right?
yeah, it depends on them.
So A will all be elements. A
Let-
will have to have integers, and up to Q it won't matter.
It doesn't matter if it's
So
more.
A will have like Z, Z,
Z,
Z, Q,
yeah.
Q, Z, right?
ZQ. Yeah. But yeah, let's forget about the parameters and everything because
Oh, this Q is not prime for?
it's not a prime. Or it can be actually it can be anything.
Oh, it's composite.
It can be composite. It can be prime also. I'm not sure whether it should be as prime.
I mean, there is no restriction.
I'm not sure. I need to look into it. But the interesting thing is that it shows that I can generate a hard lattice at the same time I can generate a short vector for this lattice. And the thing is just from LHM. So what do you do?
Hard lattice, you mean shortest vector? Finding shortest vector is hard.
No, this is hard lattice. So it's hard lattice is I give you this A. The description of lattice is just A. And then the lattice vectors are any V that takes this takes it to 0. So what he does is you take A to uniformly random from ZQ. UQ n cross n minus 1. Okay? Your last vector, column vector will be this, let's call this A dash. A dash times V, where V is chosen from 0, 1 to the power n minus 1. And your full matrix will be A dash A. So what do you want? By the LHL thing, this uniform distribution should have enough minimum. So if you remember the LHL, you needed that M.
Z is a random.
Z is a random 0, 1 binary vector. Okay? You wanted this N to be K minus, or another way, 2 times log of 1 by epsilon plus M should be K, where K is the mean entropy of this distribution. So what is the mean entropy of this distribution? N minus 1. So N minus 1 should be greater than this much. So you get a relation. Actually, we yeah, observe that the mean entropy over here is, yeah. So if you have this, if your n minus 1 is satisfying this condition, then your last vector will also look almost random. So an adversary can't distinguish this matrix from a uniformly Q raised to n cross.
How does this give us the short vector?
Simple. This z, your short vector is minus z, comma 1. It's a root n. Approximation of your
Okay.
shortest vector. So polynomially short vectors are good for us. We believe it's hard. In fact, in itis, yeah, if you can get this, in the itis reduction, when you ask for a short vector over here, it should be something like this, of root n, approximation of the shortest vector.
So what are the shortest vector?
What are they?
Like short vector as in
So short vector means the length of that vector
the
is bounded.
L2 norm.
Huh?
L2 norm.
It's an ectonorm, yeah.
Okay.
It's bounded by root n times the shortest vector. Yeah.
A prime is any matrix if
A prime is any uniformly.
and Z is random.
It's random.
Is
So
not A prime Z is random.
sorry,
Is not A prime Z is random.
it won't look that random if it is.
Yeah, I mean,
yeah.
if A prime, it depends on A.
That's what it depends on.
If A prime is all 0 0, then
No, it depends on. So A prime is chosen randomly, so it can't be like all zeros. It will become all zeros with very small probability.
no, I'm just focusing on this.
Yeah.
A prime Z.
If A prime is Z,
If Z is random.
yeah, if Z is,
Basically, you are picking random columns. And
it's
No,
not.
but it's not random.
It's
from-
0 1. It's just
Yeah.
0 1.
That
It's
is-
just picking or not picking and adding it.
It's random from a restricted space. It's not random on.
Yeah, if it's random from ZQ n minus 1, then I would agree.
Oh.
Then you're right.
Matrix elements are from ZQ,
ZQ.
not 0 1.
No, that is fine.
Mhm.
But even then, you are looking at A prime,
Mhm.
taking random columns.
Okay.
That side.
Observe that I'm not just outputting A, I'm outputting A prime as well as A n. So collectively it should look random, not just A n. That is what the extractor is doing. I'm revealing the random vectors I have been using, as well as the final vector which I'm creating from this A dash.
So AN is random.
This collision looks random. A dash plus A n. This tuple or this big matrix looks random. Yeah, so
What is the
I mean, if one column is truly random,
if which column is truly random?
AN, then if A prime is not random, then even the whole thing is sparse.
No, I'm not
Exactly.
saying so. I'm not saying
So I am just thinking if what I'm saying the statement is true, that if you take Z randomly from 0 on dash prime,
that. Okay.
then AN is random.
A n is random if I'm not showing A dash.
Sorry.
A n will be random. Okay, yeah, will look random.
Is it correct that
If you're not revealing A dash, yes, it looks random. Because you're taking a random combination of random.
exactly?
But if I'm revealing A dash also, then no.
By the way, the shortest vector, will it be this or will it be this times A dash or?
Shortest vector.
How do you know this is even in the lattice?
Because this one times this one gives me 0.
Just say A
Wait,
and
is
B
Z the
one.
product?
No, Z is this one. So what is this? So this one times this one gives you minus of A dash Z minus plus A n. What is A times this is minus A n plus A n.
Columns. Five elements.
0 mod cube.
Your A is 3 random. So well, it depends on A prime. If all is 0, then it is not random. So this is
It is
Yeah.
basically 0 comma 1 just means that you are the columns of A prime you are picking randomly.
Yes, and then adding it.
Hmm.
But imagine I have
So is not the result is random?
And A prime is completely
Even if A prime is revealed, suppose
No, you-
forget
so-
about A
so-
prime, it is 1 to 1 to
you
10.
want the distribution to look random, not just one instance. So you won't be asking the adversary just once. You'll be asking it many times.
Mhm.
The whole distribution should look not just one instance. Yes, one instance, yeah, obviously. If you give me one instance, yeah, obviously look random.
Yeah, even if
For
you are
example,
revealing A prime, that is
If
No, see,
A1 was
the-
1 0 0,
See, the following is feasible. After you give me A dash and some entries of AN, like the first few entries of AN, I can figure out which columns of A dash you picked in order, what linear combination of A dash you picked. I can feasibly figure that out if I had enough computation. And if, if the parameters were set right, which will let me figure out the remaining entries of A. For example, looking at the first few entries of A, and I might be able to figure out that, Z was like 1 followed by all zeros. I mean, I probably won't be able to figure it out.
No.
But I can probably fine-tune what I know about Z, right?
That will happen if this.
That's the issue, right?
So the issue, so if you have like lots of columns of
Yeah, if I have too many columns,
then you won't be able to do it. Yeah, kind of.
yeah.
Yeah, maybe it's a silly question. I'm very
No, it's okay.
familiar with these things.
Ashish is still thinking about it, or
It's
better?
kind of not everything I can understand.
So maybe you can take it up, right?
What was the connection with lattice?
So again, I showed that this family of lattices is hard to show. He also showed that even though it's hard, I can produce a lattice, a hard lattice along with the short vector.
But you're cheating, right? You're taking a short vector and then creating a hard lattice using the vector.
It's cheating, but no one can
I
fool.
mean,
No one
obviously, if you're
I
not
can fool
cheating,
everyone.
if you're not
That's the
cheating,
point.
it's good, yeah.
Sorry, what's the cheating?
So I'm creating the short vector by cheating it, right? Look, I'm just taking this.
Okay, right, yeah.
But this is what
Obviously.
what Elliot is saying, that I'm doing cheating over here, but I can fool everyone in the room. That's it. No one will know that whether I did this or I have a very powerful supercomputer which took a random A, computed this lattice and found the shortest vector and produced it.
It's a sacred cheating.
So it's actually to catch a cheater or something, you can say. If someone says that, okay, I have the oracle to solve SVP for this, then I will. So the problem is, even if he gives me a short vector, I don't know whether it is bounded by root 10 or something. That's again a hard problem. So I create this lattice plus the short vector, and so I know the bound of the shortest vector. So I can, if someone claims that, okay, I have a oracle, if he returns me
Something within.
this one, then yeah,
This
I
is
can
the short vector for this hard lattice, family of hard lattice.
Yeah, because
Up to this
root 10.
root and bound.
Because 0 1s, yeah. So it's a minus 1 0 and just multiply these two, then you'll get minus of a dash z plus an. An is defined as this itself, so you get 0.